Alright, a ball is dropped from a height of 10 meters and bounces back up to a height of 6 meters. Determine the velocity of the ball immediately before the collision with the ground and immediately after. Okay, so we're going to break this down into a couple different parts. We'll call the highest point part A, and we'll call the point right before it hits the ground point B. So I can refer to A and B in these cases. Alright, so we have the ball. Initially, we know the ball's velocity at A is 0 meters per second. If we let go of it, we know the acceleration will be negative 9.8, we'll just say negative 10 meters per second. And then the time we don't know it takes, but keep in mind this is the time it takes to fall from point A to point B. This is going to be important a little bit later on when we talk about the contact time with the ground. Okay, contact time with the ground is the time it takes for the ball to hit B and start going back up, not the time it takes to fall. Alright, we don't know the velocity at B, so we have no idea what the velocity is right before it hits the ground. And we know the final position at B is equal to 0. Alright, so if we look at this, we have negative 10 as our acceleration, we have our initial speed is 0, and our change in height is 10 meters, so we can use the following expression. The velocity squared at B is equal to the velocity squared at A plus 2A delta x. Alright, looking at this, we know the velocity at A is 0, so we have velocity at B squared is equal to 2A delta x. If we take the square root of both sides, we find that the velocity at B, when we substitute in 2A and delta x. Now keep in mind, A is negative, and the final minus initial. So 0 minus 10 will also be negative. So that's going to be turned out, you're going to take the square root of a positive value, not a negative value. That will equal 14.1 meters per second. Yeah, that's the velocity right before it hits the ground. Alright, so looking at this, now the ball hits the ground and starts traveling back up. We don't know the initial speed at which it leaves the ground with, so we're going to call after the collision with the ground point C, and we don't know that speed. We do know it rises up to part D, okay, and it will, if we kind of look at this in terms of a motion diagram, our change in velocity is going down. Alright, so our acceleration again is going to be negative 10 meters per second. Our time, well, we don't know. The velocity at the highest point here will be 0 meters per second, and I realize I wrote 8 here, and that should be 6 meters. Okay. So, looking at this, we need to figure out the speed it takes after it hits the ground until it gets to point D, which is 6 meters high. So we're going to use the same expression here mathematically, and we will find out that the velocity at D will equal the initial velocity at C plus 2A delta x. Alright. So we know the final velocity is going to be 0, so we have 0 is equal to C squared plus 2A delta x. We substitute everything in and solve for velocity C. We find out that the initial velocity after the collision is about 10.8 meters per second. Okay. Now we're going to look at part. Okay, a couple things here. We'll put some signs in because it's going to be really helpful when we start dealing with our impulse and momentum. Up is positive, down is negative. We've pretty much assumed this all year. My velocity errors are increasing on the way down and decreasing on the way up. So if we look at the velocity at B, we see that it's traveling down, so the momentum initially is going to be negative, and that velocity is a little bit larger than that of C. So you're going to have a large negative bar here, you're going to have a smaller but positive bar here. So if we look at a large negative value plus something will equal a small positive value, we have to then conclude that the impulse is going to be a large positive value. Alright, so we have one in each term. Our equation will end up being mvi plus the force exerted by the ground times the time it takes to interact with the ground is equal to the final momentum of the ball. Now I want to focus on this time for a second, because a lot of times people will calculate this time here or the time it takes to go back up and confuse that time with the time it takes to interact with the ground. So keep in mind this initial and final here are between points B and C, which means if they're between points B and C, it pretty much means any time that the ball is interacting with the ground. Okay, so it doesn't mean the time it takes to go up to the top, it doesn't mean the time it takes to go down, it's the time it takes to interact with the ground, which in this case is 8.08 seconds. Alright, now to then figure out the force of the ground on the ball. So if we look at this, we have to find essentially the time here. So we can subtract MVI from both sides, and we'll end up with the force of the ground on the ball times the time is equal to MVF minus MVI. Okay, if I divide both sides by the time, I get the force of the ground on the ball is equal to MVF minus MVI divided by the change in time it takes to interact with the ground, which is going to be my 0.08 seconds. So numerically speaking, this will look like the following. Alright, you are going to have, I'm going to factor out the mass here, so we're going to have 0.45 kg times, alright, the final velocity will be the velocity at C. That will be a positive 10.8 meters per second. I'm going to run minus a negative 14.1 meters per second. All this divided by the 0.08 seconds. When we essentially figure out the force of the ground on B, we find that this is going to be 139.75 newtons. Okay, that is the force that the ground exerts on the ball during the interaction.